Okay, we're doing the problems on Newton's second law. The problem states an astronaut is playing shuffleboard on Earth. The puck has a mass of 2.0 kilograms. Between the board and the puck, the coefficient of static friction is 0.35 and the kinetic friction is 0.25. The first part of the question asks, if she pushes the puck with a force of 5.0 newtons in the forward direction, does the puck move? First, we want to draw the free body diagram. There's a contact between the puck and the shuffleboard, so that gives us a normal force. It goes in the positive y direction. There's always a gravitational force in the negative y direction. And there's a force between the stick and the puck in the positive x direction, and the frictional force opposite to that, so it's in the negative x direction. The first part, we're going to break it down into the y component. In the y direction, there's positive n and negative mg, which is the gravitational force. N minus mg equals 0. We move the mg to the other side, leaving us with n equals mg, and we fill in the givens, leaving us with 19.6 newtons. We use that 19.6 and to plug it into the equation for static friction. We use the coefficient of static friction, 0.35, and we multiply it by the 19.6 newtons, leaving us with 6.86 newtons. The puck will not move because 5.0 newtons is the force applied, while 6.86 newtons is the frictional force. Since 6.86 newtons is greater than 5, the puck will not move because the frictional force opposes the movement of the puck. For part B, it asks, as she is pushing, she trips, and the force in the forward direction suddenly becomes 7.5 newtons. Does the puck move? The puck will end up moving because the force is greater than 6.86, which was the frictional force from the first part of the question. The frictional force opposes the puck movement, but since 7.5 is greater than the frictional force, the puck will end up moving. For part C, it says, if so, what is the acceleration of the puck along the board if she maintains contact between puck and stick as she gains her footing while pushing steadily with a force of 6.0 newtons on the puck? Okay, so for this part, we break down the x components, which will be equal to mass times acceleration. The x components are the force and the frictional force. Since the puck is sliding, we will use the kinetic friction. So it's F minus the kinetic friction force equals to mass times acceleration. We use the same equation that we used to find the force of the static friction, and we find the force of kinetic friction. We use the N. Like earlier, the N was 19.6 newtons, which is also equals to mg. So we replace the newtons, the normal force, with mg in this equation also. We take out the m from the side to get acceleration by itself. And since the force is 6.0 newtons, we put that into this equation, giving us 0.55 meters per second squared. That gives us the acceleration. The last part of the question asks, she carries her game to the moon and again pushes a moving puck with a force of 6.9 newtons forward. Will the acceleration of the puck during contact be more, the same, or less on Earth? So what we do for this problem is the gravitational force is 1.6 newtons per kilogram. We use that same acceleration formula we used in the previous problem, and we plug it in, giving us 2.6 meters per second squared. The frictional force is less, so acceleration due to gravity is more. So the acceleration would be more on the moon.